CCTV is very educative, informative, and there are football sport there. There is entertainment. There are a lot of things you can even attend lectures here. All you know is watch all those nonsense artists and do nonsense, or you watch nonsense on TV. Last night you almost came in bed with your fist.
It's not me, sir.
And you wake up every morning, the bed will be so rough, like you'll be fighting kung fu in your dream. That's the reason why you have F's in your courses, like especially made for you.
I have it last semester.
We E by pounds on you. Very stupid though. We are changing that section to CCTV right now. And oh God, the baby to what the first born. Stupid boy.
Hello class. We've just looked at the second lecture. We want to go straight to the third lecture. Here I want to introduce you to the concepts of induced topology. Induced topology. You want to see how you can obtain a new topology from an existing topology. That is what this course today will be all about. And then from there, we'll progressively look at the application of topology in continuity and other concepts which we see in functional or real analysis. Let's look at induced topology. This concept has other two names, namely subspace topology, subspace topology, or what we call the relative topology. Okay? In this case, we want to determine how we can get new topology from an existing topology. It's very, very simple. First of all, we know that we can have a topological space. A topological space. And when we have a topological space, X for X, that is a topology on X. You can have another set, Y, and you may decide to obtain an induced topology, or what we call a subspace topology, or a relative topology of Y with respect to X. Let's see what I mean by this. I mean that let X be a topological space. Let X be a topological space. Now, we know that the topology of X is made up of open sets. Then, if Y, or let me say A, is a subset of X, we want to determine a new topology with respect to A. So we say the topology of A here is going to be defined by a class of all open sets, intersect A, such that U here belongs to the topology of X. So when this happens, what it implies is that A is an induced topology on X. So we obtain the topology on A from X. Now, so A is a relative topology of a Tor X. I'll give an example. Consider X equals A, B, C, D, E with a topology Tor X given by empty set X itself, singleton A, AB, ACD. Please permit me to rub off this and to continue. Now, so that we have A, B, C, D, and then A, B, E. Okay, so this is a topology on X. Now, we want to obtain a new topology with respect to A. And let A here be the set A, C, E. If you want to obtain an induced topology on A from X, what do? We simply obtain, say, all these are empty sets. What is the intersection between an empty set and A? That is an empty set. Now, secondly, what is the intersection between A and X? Of course, we know that A is a subset of X. ACE is a subset of A, B, C, D, E. Because you can find ACE, ACE here. So the intersection between X and A is A itself. Because the whole of A is in X. So now the next thing we consider is the intersection between ACE and A. We simply have A there. Intersection between A, C, D. Okay, let's look at this. With AB still A, with ACD, that is AC. Intersection between ACE and ABCD is still AC. And then intersection between ACE and ABE, what is that? That's simply AE. You will agree with me that what we have here are all subsets of this. They are all subsets of A. A empty set is a subset of this. A is a subset of itself. A is here, AC is here, and AE is here. So this is a new topology. So you can obtain a new topology from an existing topology. And when you do that, we call that a relative topology or a subspace topology. Now, having done with that, the next thing we want to look at is what we call basis and sub-basis of topology. Basis and sub-basis of topology. Now, when we talk about basis, we are talking about the building blocks of topology. You need to pick smaller, just like the human body or any living organism is made up of tiny, tiny cells. The cells, the aggregate of the cells make up what we call the organism. Similarly, in topology, you can have the aggregate of smaller sets from, coming together to form what we call a topology. And that is why we call it the basis of a topology. So let's quickly take a look at that. Now, basis and sub-basis of topologies. Okay. Now, when we talk about basis, we want to define what a base is. Let X be a topological space. Of course, when I say X, I told you earlier that X is taken to mean a pair of X with its topology. That's when it is called a topological space. A family or class, which I denote with curly of open subsets of X is a base for the topology for X if and only if it satisfies these two axioms. Number one, every open set into X is a union of members. Let me call these members capital B, which belongs to the base in the family. Okay? They call this BJ. That is, U is written as a union of BJ, where each BJ comes from the family here. So this BJ forms the building block of the open sets. Number two axiom that a base must satisfy. Number two axiom that a base must satisfy is that for any point P, you know, we are considering point set topology. So you don't just talk of the set in isolation. You must consider the point. For any point which we find in the open set U, there exists a base in curly B with P belonging to that base in such a way that that base there, okay, will always be a subset of U. So we say that a base is satisfied if it fulfills these two axioms. Let's take a look at this example. Okay, example. Let X be a triple member set, we show that curly B here, which is made up of the pair AB and BC, here cannot be a base for any topology of X. So with what we are going to have, we want to look at the axiom to make this proof. Now, if this must happen, if curly B here must be a base, then for AB and AC will certainly be, elements of any topology, okay? I'm casting a shadow, okay? I believe you have a better view here, okay? Now, so you can see, if we want to assume that this is a base of tau X, then must these two be members of an open subset, which of course, of the topology on X, which of course is a subset of the power set of X. And the intersection of A, B, and intersection of AC is the singleton A, okay? And, sorry, this B. It's B here, please. So the intersection here is B. Now, and is, of course, by the axiom of a topology, this B should also be here. But let's note that not the union of members of curly B. Now, what does this mean? From what we have here, we claim that every open set here must be written as a union of the bases, okay? Must be union of the bases. Now, if you take a union of this and this, you will get X, of course. That's true. B here is a point, okay? And if B here is a point in X, isn't it? There exists a B in the basis that contains the point B here, and of course we know these are elements in the basis for which at least one of them must be subset of U. So this is what we see here, that this is an open set, and if we claim that these are the basis for the topology on X, okay, then the union of these two actually form X. And their intersection here gives us a point. But the question we want to ask ourselves is that, can we always find a point in any other open set in X for which that point will be in the basis, and then the basis will be subset of U? Let's take a look. Can we try A, for instance, singleton A? Now, you agree with me that A is in this, but it's not here. Now, if A is here, but is not in the second, can we find a limit or a limit point? Can we determine whether this is a limit point? Of course, if you take A out of this, out of AB, what are you going to get? You will get B. And if you get B here, if you take the intersection of B with any other set in X, it's obvious you might still get a non-empty set. So A can be a limit point. So, but we are not using the limit point at this definition of a base. What we are simply using is these two axioms of definition. So, from what we can see here, we can really conclude that this is supposedly a base of any topology of X. So, we proceed to the next thing, which has to do with subbases. Subbases. Let's take a look at subbases. Now, if a base is a building block for topology, it means that subbases too should be building blocks for bases. Now, let's look at what defines a subbase. A subbase definition. What defines a subbase? Let X to X be a topological space. A family, call it S here, of open sets, or open subsets of X, that is, S is a subset of the topology on X, where this is subset of that, is said to be a subbase. A subbase. If and only if the intersection of SJs Now, let me say that this S here is different from this. These SJs lie inside the curly S, okay, that we have here. So if you can write the intersection, okay, of this, the intersection of subsets of the open set this to be equals to this, then this actually is what? A subbase. For instance, let's take a look at what we have here. This is a subset of the topology, okay? And you need to know that if you pick this pair, it's still a subset of this topology. By the time you take intersection, intersection of members of the base, okay? Or let me say any two subsets of a topology. And the outcome of as many arbitrary intersection of elements of those subbase gives you a base. Look at this. This is B. B here is not found as a singleton set in this collection. And so we cannot claim that this and this are subbases. If after taking intersection of the two, you get a third set, okay, and it being B is in this set, then you can lay claim that these sets, AB and BC, are actually subbases of curly S. But that is not the case. This is where alpha here is belonging to an indexing set A. So we are done with this aspect. Now, I want to quickly introduce us to the concept of continuity. The concept of continuity is a very important concept when you come to analysis of any kind, be it the real analysis or be it functional analysis. Continuity is a concept that is very important in analysis. And we have a way in topology of defining continuity that I will quickly show to you today. Okay. So let's look at continuity. Continuity. Now, in elementary analysis, the concept of continuity forms the bedrock of modern mathematics. Of course, you cannot talk about differentiation without continuity. You can't talk about integration without continuity. You can't talk about other concepts that take their building block from this concept of differentiability and integrability without the knowledge of continuity. Now, before we define continuity, we will need two topological spaces. So, you say, let X and Y be topological spaces, and F be a map from X to Y. Then, F is continuous. F is continuous if and only if given U belonging to tau X and V belonging to tau Y such that F of U is a subset of V whenever U is contained inside the subset of F inverse of V. This definition is different from the delta epsilon definition, which students at elementary analysis class come across, but is the same thing. We are saying the same thing using a different language. So, let me give you an instance. In elementary analysis, we define continuity of a function as in elementary analysis. A function, please accept my abbreviation, a function f from x to y, okay, most times this in a real analysis, okay, so, okay, we always map x to the real line. So a function this is continuous if and only if given epsilon greater than 0, which sometimes we write as epsilon belonging to the positive real line, there exists a delta, a positive delta 2. We can also say it belongs to real line, positive real line, such that the modulus of f of x, okay, is continuous at, let me put, at a point x naught here. At a point x naught, if and only if given epsilon, a positive epsilon, there exists a delta positive epsilon such that f minus f at x naught is bounded by what? Epsilon whenever x minus x naught is bounded by delta. I want to show us that there's possibility of writing this in this form. And that is the possibility we are trying to look at here. In this case, we are taking a specific case, but here we are having a general case of continuity. So that is the difference between them. And this kind of continuity is on the what we call the Euclidean topological space of the real line. I will teach you that in the next class. So, but let's see how we can put this in that form. This particular inequality that we have here can be written as minus epsilon less than f of x minus f at x naught less than epsilon. Okay? And this can also be written as delta less than minus x naught less than positive delta there. Okay? Now, if I decide to add f of x naught across, we have this. This f of x is bounded below and above by this. So I've added f of x naught here, added it here, cancel this, and added f of x naught here to obtain this. If I do the same here, what do I have? I have x naught minus delta less than x naught plus delta. What did I do? I added x naught plus x naught plus x naught, and that is what gave us this. Now, this can be located on the real line, on a curve, and this also can be located on a real line. So we can simply depict this. We can depict this as the neighborhood, open neighborhood of f. The open neighborhood of f is the same thing as saying that f here lies in this open set. And this I may decide to write as v here is the neighborhood of f. Okay? V here is the neighborhood of f, and it is made up of the open interval fx minus epsilon, is fx naught minus epsilon, comma, fx naught plus epsilon. Okay? And then I can also call this one the delta neighborhood. Okay? The delta neighborhood of x. Okay? So I call this one the epsilon neighborhood of f. I call this one delta neighborhood of x. And so I get x naught minus delta, x naught plus delta as the lower and the upper bound there. So if you now look at this, you simply put that f lies here whenever x lies here. And we are there. So, because x lies within this neighborhood, whenever x lies within this neighborhood. So this here is the delta neighborhood of x. So what we've simply done here, this is just a particular case of the general case. So that is why this definition is more general. And both this and this are both topologies belonging to the topology on R1. That I will tell you in the next class. I need to give a few other definitions that is required. We have what we call the continuity at a point. Continuity at a point is what you see here, but I can decide to give it in general, okay, by saying that f is continuous at a point P. Okay? If P here, let's say that P is in X, if and only if the inverse of every point of every open set V contains P. That is, P belongs to the inverse of the map of every open set where V belongs to tau W. Okay, I mean tau Y. Okay. So when this happens, then this is whenever we have f of p belonging to U, where this U is in the topology of X. Is in the topology of X. So that is continuity at a point. Apart from having continuity at a point, we can also have a sequential continuity. Sequential continuity. So that will give us what I'm about to say now. Let me just introduce what we call sequential continuity. Our students of elementary analysis have done sequences. You have done continuity in a sequence, but in this course, you are going to see how we define sequential continuity in topology. So, definition: sequential continuity. Okay? Here we say a function f takes x to y is sequentially continuous. Sequentially continuous at a point P. This P is in X. Okay, mind you, if and only if every sequence of points, some texts call it net of points. Every sequence of points in X converge to a point P. And the function of this sequence, okay, converges to f of p in y. Okay? So what is this simply saying? That the continuity of a sequence implies continuity of that sequence in a function or in a map. So that is what sequential continuity means. So we are done with continuity today. At the next class, we shall be looking at equivalence of topologies, and that will conclude the basic concepts of topology. After this, we will now go into the core concepts of topology. Thank you very much. If you have any question, contact me through my WhatsApp. Thank you.
Finish him. Kill the guy now. You have to go. Beat him.
What? What is this?
Good day, sir.
You are watching Jackie Pan in my house.
No, it's King Kong, sir.
King Kong. You've never heard of ACTV before in your life? ACTV is very educative, informative, and there are football sport there. There is entertainment. There are a lot of things you can even attend lectures here. All you know is watch all those nonsense artists and do nonsense, or you watch nonsense on TV. Last night you almost came in bed with your fist.
It's not me, sir.
And you wake up every morning, the bed will be so rough, like you'll be fighting for in your dream. That's the reason why you have F's in your courses, like especially made for you.
I have V last semester.
We eat by pounds on you. Very stupid. Oh, yeah, change that section to ACTV right now. And oh God, the people to have been first born. Stupid boy.